Hello, my people. Let's go ahead and jump right in with another couple of examples on average function value and mean value theorem for integrals. Let's say that I'm given f of x is equal to 4 over x squared, negative 4 to negative 2. Now remember, that is a function which looks something like that, okay? Now, because it's squared in the denominator, we notice that whereas the original was, the original reciprocal function has origin symmetry, this is going to have y-axis symmetry. This is even. But let's go ahead and just jump right in. I know that if I have 1 over b minus a, integral from a to b of f of x dx, that should give me the average function value. Now notice notice that I've changed it from a denominator to a negative exponent because I'm going to need it in that form in order to do the integration. But this over here, I mean, and the thing is that it's probably easier just to say from negative 4 to negative 2, that's a width of 2, so I need to be multiplying by 1/2. I need to pull this 4 out as well, and so if I pull this 4 out and combine it with the 1/2 out in front, I'm going to get 2, okay? And then I'm going to integrate x to the negative 2. X to the negative 2 becomes x to the negative 1 over negative 1, so negative x to the negative 1 from negative 4 to negative 2. Now it's probably a little bit easier to think about it like this, so we'll put it in fractional form. And when I plug in this one, when I plug in my my b value, okay, I'm going to get negative 1 over negative 2 minus negative 1 over negative 4. And that winds up doing a whole lot of negative cancellation. And I get 1/2 minus 1/4, which is of course 1/4 times 2, which is 1/2. Okay? That is the average function value for this function on this interval. Okay? And if that was all I asked you for, then I would certainly just want you to stop right there. But let's go ahead and ask the mean value theorem for integrals question of if that is the average function value for that function on the given interval, what for what value or values of c within that interval does the function value equal the average function value on that interval? And you simply need to, set the function with a c instead of an x equal to that average value. And a little cross multiplication gives me c squared is equal to 8, and therefore c is equal to plus or minus 2 root 2. Well, positive 2 root 2 is not going to be on the interval, but negative 2 root 2 approximates to negative 2.828. Okay? That's kind of an easy graph to think about and an easy function, so I'm not going to do the calculator legwork to show you that one. Let's go ahead and move on to the next question. Let's go ahead and let's do a radical function. F of x is equal to root x, and we're looking for the interval 4 to 9. Okay, let's look for the average function value from 4 to 9. I know that it's going to be 1 over b minus a from a to b of x to the 1/2 dx. So if I have 1/5, and let's go ahead and integrate x to the 1/2, it's going to be x to the 3/2 over 3/2, or 2/3 x to the 3/2. We're going to be evaluating from 4 to 9. Now let's go ahead and pull out that 2/3 and combine it with the 1/15, and I know that's going to be 9 to the 3/2 minus 4 to the 3/2. Those are actually pretty easy to evaluate because the square root of 9 is 3. 3 cubed is 27. And 4, square root of 4 is 2. 2 cubed is 8. And so what we have here is 2/15, 27 minus 16, okay, which is going to be 2 over 15 times, no, that's 8, sorry, 19. Okay, that is 38/15. 38/15, as odd as it sounds, and as odd of a number as that is the average function value for this function over this interval. And if that was all I asked, if I only asked you for the average function value, you would stop there. But let's say I ask you if mean value theorem of integrals applies. Well, I mean, remember that there is, just like the original mean value theorem, there actually is one condition that needs to be satisfied. And basically the function needs to be continuous on the interval. That much we've already confirmed. It's radical function. It's continuous on its whole domain, which is 0 to infinity. And 4 to 9 certainly falls within that. But basically what I need to do is I need to take the function f with the c value, so f of c, and set it equal to that value. Now, it's going to be ugly when I square that, and so I'm really not interested in actually squaring 38. I mean, I know what 15 squared is, but 38 squared is kind of obnoxious. I mean, you could easily get there from 40 squared and then step back down from there. But it doesn't really need to be done like that. You're going to be looking for a decimal approximation anyway, because even if you were to square it and actually get the correct and proper fraction that represents that, it's going to be a little bit more difficult to figure out exactly what that number represents, what its true value is. And so the true value is somewhere around 6.418 when you plug it into your calculator. And that is on this interval. And that kind of makes sense that there's only one, because remember that, you know, the radical function is always increasing, right? It's not going to dip back down. And so, you know, if you go from 4 to 9, okay, and, you know, it's going to be somewhere right about there, okay? All right, let's do another example. We haven't gotten to transcendental functions on this, so let's go ahead and do a transcendental function. Remember, transcendental functions are those functions that are not algebraic, meaning they have nothing to do with polynomials. They're not algebraic in their form. They thereby transcend algebra. And that includes, you know, exponentials and logarithmics and trig functions and stuff like that. So let's go ahead, and we want to find the average function value for sine x on 0 to pi. Okay, well, let's go ahead and do that. So we have 1 over b minus a, the integral from a to b of f of x dx. And that's 1 over pi. And when I integrate sine x, it becomes negative cosine x, and I'm going to go from 0 to pi. Okay, well, 1 over pi, and basically that becomes negative cosine pi minus a negative cosine of 0, and that's 1 over pi, 1 plus 1, or 2 over pi. Well, that's easy enough, right? And, you know, if you wanted to approximate that, it's right about 0.637. And that would make sense because 2/3 is 0.667, and so that's 2 over a denominator that's a smidge larger than 3, and so this would be a smidge smaller than 0.667, okay? Now, here comes the fun part. Let's go ahead and ask ourselves, what is the c value that makes sine have an output of 2 over pi, okay? And of course this, you know, this is a decimal approximation. its sine of c is, equal to 0.637. But I want to do this. I want to basically plug it into my calculator. And of course, your calculator doesn't say arc sine, it says, inverse sine. But I want to plug it into my calculator with the exact value. And when I do that, I am given 0.690 as a value, okay? But not so easy, okay? Let's go ahead and redo this for trig. Sine x, and I know that 2 divided by pi, let's go to the window, and let's go 0 to pi, and let's do, I don't know, pi over 6 as, and let's go -1, let's just go 0 to 2, so we can actually just see the whole thing, okay? And, from what we know about the sine function, it's just that first hump right there. Okay, well, there's the 0.69. Uh-oh. I have two values, okay? Well, let's confirm the first one first, okay? Let's go ahead and find the point of intersection. And it says 0.690, okay? And that's what we have here. So let's go back to the main screen, okay? And remember that basically in order to get that, we were looking for this. The problem is that your calculator is not set up to give you two values. And remember, the inverse sine function has a certain domain and a certain range. It's up to you to extrapolate from that what the other value is. And you can think about it in two ways. You can think about it in terms of the graph. We remember that there's a symmetry here, right? At pi over 2 would slice that in half. So this point right here, this point of intersection, is just as far from the end of the interval as this point is from the beginning of the interval. Oh, sorry. Let me move that over like this. I didn't realize it was shining from the lamp above. This point of intersection is just as far from pi as this point of intersection is from 0. So basically it's just pi minus that c value is my other c value. You can also think about it in terms of the unit circle, right? Remember, when you're dealing with inverse trig on the unit circle, you're taking this value and you're kind of going, okay, where does sine have an output of 0.637? Well, at that angle, right? And that angle, right? And if this is theta, then this right here needs to be pi minus theta, because that's also measures theta, the reference angle right there. And so our other value is going to be pi minus 0.690, which is basically 2.451, okay? So your c values are both of those. And let's go ahead and confirm that. Let's go ahead and find the point of intersection. Okay, get close to the point of intersection, enter, 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 and we do indeed get 2.451, just like we did when we subtracted the original c value from pi, okay? So when you get to the trig functions, because of the limitations of the algorithm for the inverse trig functions, you just need to be careful that you're giving me all of the values that you can give me, okay? I tell you what, I'll do one more video, and we'll be done with this. I just want to do, I concentrated primarily on the polynomial and the rational and the radical for the first two. I want to get to a couple of more difficult ones. Some of them will require the calculator, some of them will not. But let's do one more video, and then yeah, I'll look forward to fielding your questions when we get together on Tuesday, depending on how many of you are there. I know several of you have several of you have your thesis presentation on Tuesday, so whoever is there, I'll see you there. Otherwise, I'll see you on Friday, okay? If you're not there and you have questions on this, send me any of your questions by message, by chat on Teams, okay?